So welcome to lecture 20 of MCS 471, numerical analysis. So this is the third lecture on least square problems. So we are solving linear systems in the least square sense. So this is a lecture on numerical linear algebra. It is the third lecture on least square solving. In lecture 18, we saw that least square solving corresponds to a QR decomposition of the matrix. And in the last lecture, we considered two methods, the Gram-Schmidt method and the householder QR, to construct a QR factorization. So the topic for today, and I'm underlining it here, is that we will go to consider iterative methods. So you see also on the slide the names Jacobi and Gauss-Seidel again. So this is another way to tackle very, very large problems for which the direct solvers no longer apply. So in doing so, in arriving to get to the generalized minimum residual method, we will see the power method to compute the most dominant eigenvector and the largest eigenvalue in modulus. So let's start first by considering spaces spanned by matrix vector products. So the setup is that we have a linear system where we have a right-hand side vector and some algorithm to evaluate the matrix vector product. So the matrix may be defined by a formula that decides on some pattern. Now we have an efficient evaluation. So the evaluation could also be linear in the dimension. So that was the big selling point that we also had for the conjugate gradient method when we considered the solving of very large positive definite matrices. Now consider what can we do? Well, we have an algorithm to evaluate A times X. Well, that is what we can do. So we start with some vector, and we could take the right-hand side for whatever. So the right-hand side, as we will see, will correspond to taking start value 0 for the solution, as good as any. So we will take products of a vector with the matrix A. And that is stored in the columns of a matrix called K, so to honor Krylov. So we can write that product. So if we now are going to compute the next product, so you can see Y1 is A times. So the indices of the vectors actually correspond to the powers, so powers minus 1. So this vector here, the last vector, is actually the vector y5. And this is defined by taking A times the previous vector, or we can also now rewrite this last vector in terms of the first vector. Why is that useful? Well, then we have a relationship between the four vectors y1, y2, y3, y4, and the relationships in linear algebra are expressed by matrices. So we can derive the A times K matrix as K times another matrix, where we get in the last column the coefficients of y5 of the last matrix vector product. So if you would do this computation of the next vector, you would not do the matrix vector product. But the matrix vector product is extremely useful to give an interpretation of what it is that we are going to. So we have a special matrix. We have the bold C here, which can be explicitly derived. We have the coefficients of the last vector, a to the power 4 times y1, sitting in the column of this matrix, that is the last matrix. And we can define an explicit formula for this last, for the coefficients. What is actually important is that the matrix that expresses the relationship between these two spaces. So we actually are taking the column spaces of A, we are making another subspace, that the matrix that combines these two. So the matrix, we have the Krylov space, but then we have this companion matrix. And the companion matrix, you may have seen it or in the linear algebra course, but this matrix is related to the roots of a polynomial and also the roots of the characteristic polynomial of a matrix. So here you have A times K equals K times C. So we have K times at the left and the right. Remember the eigenvalue problem. A times, so an eigenvector pair is a pair of a vector and a number where multiplying the matrix by the vector gives you a multiple of the vector. So the shape in which this can be brought into will actually lead us into eigenvalues and eigenvectors. So this last column of this Krylov space actually converges, or actually all the columns actually converge to, as we shall see, the largest eigenvector, or the eigenvector with the largest eigenvalue. All right, so here's some definitions. So the columns of the matrix K, they define a Krylov subspace. Now, if you would compute these products, at some point you would stop at some little k, because you might notice that these numbers are starting to grow very rapidly. So you will need to rescale, but a better way to make everything look nice is to compute a QR decomposition. That is to compute an orthogonal basis of the columns of K. And that can be done what we'll do in this lecture, we will do this with the Gram-Schmidt method. So in some sense, we are applying, so we can see this as kind of another modification of the Gram-Schmidt method, where actually now we give up after k steps, so we stop it. But another connection that we're going to explore now is the connection with the eigenvectors and the eigenvalues. So actually, it's already stated here at the bottom line of the slide. Where does this last column actually go if you do these products? And that will be the topic of the next part. So let's look into what is called the power method. So the power method works into the same way, the same assumptions as we started with. We have some algorithm to evaluate A times X. So we can either do this explicitly if we have the complete matrix, but it could also be given by some structured matrix. All right, so what are we after? We are after the after the largest eigenvalue. So in a way, we are giving now a constructive method to define what we called the spectral radius of a matrix. And the spectral radius of a matrix is defined as how far you can stretch vectors under the matrix vector product. So if you see the matrix as the definition of a linear map, then how far can you stretch these vectors? And it turns out that you can figure this out by just multiplying, by just taking powers of the matrix, just doing this repeated multiplication. All right, so assume now that we have all distinct eigenvectors. That is in the case for most matrices. So then we can write the vector we start with as a linear combination. So here we have a linear combination of the eigenvectors. So any vector can be written as a linear combination of these eigenvectors, and then see what happens to these coefficients if we multiply. So now, why did we go to this representation? Well, we can use the property that all these eigenvectors can be simplified. So the product can be simplified, the eigenvalues come. So, and the eigenvalues are, so this eigen is a German word, but it's the translation in English would be the proper. So these are numbers that are important characteristics of the matrix A. So that's also why I talked about the characteristic polynomial in linear algebra. So they are saying something fundamental about the matrix. So if we are rewriting now, if we make a step from one product to the kth product, then we can repeat this simplification here, exploiting that we have an eigenvector eigenvalue pair, and come at this relation here. So if we have the eigenvectors, you could also see this. If you would have the eigenvectors and the eigenvalues, you would actually have a simpler way to compute this power of k times x. Now, we can actually use this to further factor out the largest eigenvalues. See, here by convention, we have labeled all the eigenvalues and the corresponding eigenvectors such that the eigenvector with the most largest eigenvalue in absolute value comes first. Now, if you factor this out, then you can see that if the lambda 1 to the power k, this just becomes 1. But here, suppose that lambda 1 is twice as large than lambda 2, then the kth power will just make that number go away. So after 10 times with 1 power, you're already seeing that the contribution of the second eigenvector in that product is going to be very, very diminished. So what we have on this slide, we have actually shown that in the limit, or actually not so much in the limit, already after a couple of iterations, that vector will actually converge to V1. So actually the slide is not really complete. So actually I should have indicated that a to the power k times x converges or becomes parallel to V1. So vectors are only determined up to some constant. So it will be parallel. All right, so here it is stated then. And this actually gives the algorithm to find the vector corresponding to the dominant, to the largest eigenvalue, also corresponding to set the dominant eigenvector. Now this is a mathematical algorithm. what you may want to do in the practical algorithm is actually scale. Now, how do you actually find the magnitude of this dominant eigenvector of the largest eigenvalue? You take norms. So here you have the formula. So you have to normalize to this computation. So it's important that you normalize. And here you see also the relationship with the definition of the spectral radius. So we defined the spectral radius as the largest ratio in norms of A times one vector over that vector. And it's obvious now that this corresponds to the largest eigenvalue. All right, let's define this in Julia, because we had formulas, we didn't yet have an algorithm. So it's an iterative algorithm where the convergence will be linear, but we'll see how we can make very fast converging and very slow converging iterations by picking the eigenvalues of the matrix. Here we have the description of the parameters. So two parameters essentially, the matrix and an initial starting vector, and then three parameters with default values. We have a tolerance, a maximal number of iterations, and then there is the verbose option. All right, the algorithm fits in its entirely on one slide. So in order to look for the convergence, we will actually have a triplet here with the current approximation for the dominant eigenvalue, the previous one, and then the error. So we will actually print out the progress. And what is new here, or actually we introduced it when we were computing the spectral radius with the norm of the dominant eigenvector. What is actually new here is actually that we do the norm of x. So actually each time we compute the norm of x and we renormalize. If you would not do this, you would still have a mathematically correct algorithm, but the numbers would actually grow very, very rapidly, and you would introduce a lot of round-off error. So you would think that everything is actually diverging. So the algorithm itself consists of two steps, the matrix vector product, and then the normalization of the vector. So there actually are two steps. So this is a very basic, very simple algorithm. Let's run it. So let's run this on a random 4x4 matrix. And what you should check is the progression of the error. You see the error progresses, goes from something that is 2 point to an exponent that is 10 to the power minus 3. And we also print out the eigenvalue, so the magnitude of the eigenvalue. You can see as the error is 10 to the power minus 3, I can here underline the number, the decimals that are corresponding between one step and the other. So the error 10 to the power minus 3 corresponds to 3 decimal places that we get correct. All right, so let's continue a little bit. The tolerance was 10 to the power minus 4, and we are getting there. So this is a linearly converging algorithm because we need a couple of steps. So here, 3 steps to get 1 extra decimal place. And from this random matrix, we get the dominant eigenvector, and we also get the spectral radius. I probably should leave it as an exercise. The eigenvector can actually, the eigenvalue can also be complex. So we are doing real arithmetic here. So we will not find the complex eigenvectors. And also the radius itself, it's a positive number, but it could be that that is a negative number. So as an exercise that I forgot to assign, I could actually indicate, can you find the sign of the eigenvalue? How would you check that the eigenvalue is actually negative? Think about this. So the convergence is linear. That's for a random matrix. But if you remember the analysis that we did, how we got to the power method, I mentioned that if the second eigenvalue is twice as small as the largest one, for example, if in this case here the ratio is 1/2, actually that will determine the speed of the convergence. So if, for example, it is 1/2, then actually your error will be cut in half. So let's verify this. We can actually make matrices with very large eigenvalues. It's the same recipe that we have used for matrices with very large condition numbers. So condition numbers are defined by norms as well, and you can see how the spectral radius is actually now used to define the condition number of a matrix. All right. So we have here a matrix constructed. So we constructed a diagonal matrix, and then we have here an orthogonal matrix. So it's not written in words, but it's written with the property. Then by the relationships, so if we have made the matrix in this fashion, then we have this relationship here. So A times the columns of Q equals the multiples of the columns of Q. So we have eigenvectors that are unit vectors. We have already a basis, an orthonormal basis of the column space of A, and we have eigenvalues that are prescribed. Verify this in Julia. This is an interactive session where we make our matrix A, then we compute the eigenvalues of the matrix. And we see the 1, 2, 3, 4, 5 as the largest eigenvalue popping up. All right, then, here is the exercise now, the first exercise. Put the statements on the previous slide, so the making on the previous two slides. Put the making, so actually it's only one slide. Put this in a Jupyter notebook and run the power method. So also copy the Julia function for the power method and run this. So how many steps will it take to converge? Now the ratio of, so this will be in some sense a very boring exercise with the default tolerance, because what you have is that 1, 2, 3, 4, 5 is a 6-digit number. So the ratio of the largest of the next to largest eigenvalue. So lambda 2 is 1, and the largest eigenvalue is 1, 2, 3, 4, 5. So, and this is approximately 10 to the power minus 6. So actually your convergence will actually be extremely fast. So you should still see that the convergence is actually linear. So the factor by which the number of decimal places grows is still constant. Of course, with the floating point, the 64-bit floating point precision, it may not happen. We still have a constant number of steps per additional correct decimal place. Now that constant number may actually be a fraction. It may be that in one step you gain much more than one decimal place. So I am at least talking to the explanation. So the explanation is actually the ratio over the second eigenvalue over the largest eigenvalue. This also kind of explains why on a random matrix the convergence was actually rather slow, because on a random matrix the eigenvalues will all be rather of the same magnitude. This is a constructed example where you have kind of fast convergence. And you can actually also see that for orthogonal matrices, this method will actually spin around because all the eigenvalues on an orthogonal matrix are actually 1. So running the power method on an orthogonal matrix might not really give you that much. Although that could have been an exercise to another exercise that I could have assigned. What happens if you run the power method on an orthogonal matrix? We have an exam coming up, so there are many extra exam questions that I can ask. All right, let's now go to the actual topic, how to solve linear systems in the least square sense in an iterative way. So let's do this with a very simple idea here, but actually the idea is, well, the only thing that we can do is actually our matrix vector products. So we can no longer, and preferably these matrix vector products should be on very structured matrices, so that they actually are not quadratic even. So for very large problems, even quadratic cost might be a bit prohibitive. So we now know where this vector goes to. So that's already something. So we start now not with the vector b, but we have some x naught. That's also something where you kind of assume in the setup of iterative methods that you have already solved some system with a similar structure, or you have somewhere a good guess. And then we start not with the right-hand side vector, but we start with the residual. All right, so then what is the idea? Well, we add one extra vector, and we will re-orthogonalize the basis with Gram-Schmidt. And then we will use a least square method. So when we were doing the least square solving with Gram-Schmidt, we will first constructing a QR, and then we will doing one least squares. Here we will orthogonalize in every step. So in every step we subtract the projections. So that's just a modified Gram-Schmidt method, but we will actually solve a least square problem in every step as well. This sounds prohibitively expensive, but the matrices are very small inside relative to a very big matrix. On our examples, this will not be obvious, but in application areas, we have huge matrices and we work with a small least square set. So we're going to minimize the residuals. So you can see where the method comes from. So the residual in the name of the method comes from taking the residual and constructing this Krylov space. Here is the pseudocode, which serves well to kind of define again the setup. So we have an iterative method, and the number of iterations should actually be less than the number of columns. So in our examples, we will go up to the number of columns, and that is actually then equivalent to solving the original least square problem. What you may recognize here in the steps in the innermost for loop is actually the Gram-Schmidt process. So we make inner products and then we subtract multiples of the inner products, multiples with the vectors q. So the q vectors will define the orthogonal basis for a subspace of the columns of A. So the half of the method is already explained by the Gram-Schmidt orthogonalization. Then the setup of the least square problem. So the least square problem is over here, and we are minimizing the residual. So in a way, the way the problem is set up may also, if you remember the last lecture, with the householder reflector, where we normalized a vector, and then we constructed a vector where the first coefficient was actually the 2 norm, and the rest were all zeros. So you can see this also as fine as a very similar move that we did today, that we did in the last lecture. So instead of using the r's for the coefficients of the inner product, we are using h as the letter. The h stands for the upper Hessenberg matrix. So this is another special type of matrix. So there are 3 steps in this algorithm. We have the reorthogonalization, we have the minimization, and then we have the update. We do the update to the x0 vector. All right. The definition of this H matrix. So what is the interpretation of the coefficient H? Well, for this slide here, the matrix A is actually a square matrix. So we will see in the Julia code how we can fix this. Starting with the square matrix seems to be a little bit odd, given that one of the virtues of considering least square solving is that you can deal with over-constraint problems, but we will fix that. Here and actually you can see that there is actually also a little bit of a problem already here if you would see this. But let's check this. So here we have k plus 1 columns, and the q's are all of the same dimension. Here this matrix has k columns, but it has k plus 1 rows. So if you do a matrix vector product, then the columns here, k plus 1, must align with the rows. So the rows here, I should have highlighted this, the rows here are k plus 1 as well. Okay, so let us now look at what these HKs are. Well, the H2 here, this is used in the product of the second row with the second column here. If you look at the left, we have our matrix, which is an n matrix. So the same number of rows here. So the n is a number of rows. So the number of rows matches. And here we have k columns. So the k is k here. Perhaps I should have flipped other colors. So not have used the same color all the time. But you can see that the shape of this matrix actually works outline. We defined the h case, these coefficients, as the product of the q's with the a's. So you can also kind of see that the a times q1 comes back here when we have coefficient h1, 1. So in a way, this is the matrix. This is the making of this matrix A, H. So in shorthand, this is written like this. So in the Julia program, if we are seeing, so what follows in the slides I'm trying to explain now is kind of both the explanation of the idea of the algorithm in the pseudocode and the actual code, Julia code. So we will have a matrix A and we will have a matrix Q that we are making. The Q will represent the orthogonal basis in the Krylov space. The H is an upper Hessenberg matrix. And let us not forget that this is an iterative method. So how do we augment now the x naught? Well, we can write any vector in as a linear combination of the basis elements. So we're going to do this coefficient vector. So we're going to look for a vector that is in that space that actually is minimizing the residual. So we want to solve this linear system still, but we are using only the first k columns. And we are using the an orthogonal basis spanned by these columns. So in formulas, we can do the minimization here of the residual. And minimizing the residual means that we solve in the least square sense. So we are minimizing this objective here. And it will turn out that we will rewrite the delta x in terms of the solving. So here we compute delta x in basis q, and it will turn out that this will minimize the least square error of the matrix H. Okay, so on the previous slide, we are actually using this relationship here, that A times QK is Q times with the column added and the Hessenberg matrix then. All right, let's move forward. So the slides have the disadvantage that everything is one after the other. It's often good to see the three slides next to each other because they are interrelated. So we have already the structure, we've seen the structure again with the upper Hessenberg matrix. So the fact that this is kind of, that this has this upper Hessenberg structure with one extra diagonal, if you like, and one extra row comes from the fact that we are adding one extra column to our Krylov space. and we are actually always adding one extra row to it, and also computing all these additional k coefficients. So we want to minimize the residual factor, what we need to add to x naught, and this is expressed as solving this over-constrained system. So we have k plus 1 equations in k unknowns in the least square sense. And this is the algorithm explained, so I just from the previous slide. So here we have this now in shorthand. So this is the step explained for what was in the pseudo code explained on the previous slide. There is a stopping criterion. When we have that the last element on the last row and the last column of the Hessenberg matrix is 0 or is very close to 0, then that is an indication that we have actually reached the exact solution of the least square problem. All right, so it's an iterative method. We can also see how this error actually decreases. The residual is decreasing in each step. All right, so then we are ready for Julia function. So we will run a number of steps of this algorithm. The number of steps should not be larger than the number of columns. In practice, this is not a problem if you work with huge matrices. But if we run on our small matrices, we actually get quickly to that point. It's also, if you compute an orthogonal basis, then you cannot go beyond the span. So if you project any other matrix, you will actually have to end up at 0. All right, the algorithm is a little bit more involved as we need to initialize our matrices. So we have the Q matrix and the upper Hessenberg matrix. We compute the residual. So here you see that we have defined the number of rows and the number of columns. So this Julia function is more general than the pseudocode. It accepts non-square matrices. And here is the fix. So you can always turn a matrix that is not square, that is rectangular, into a square matrix by padding with zeros. In some sense, this is also what was done here. We are selecting only those variables that are corresponding to the columns. So the x naught, the residual vector, is actually a vector that is as long as the number of rows. So if the A has fewer columns than rows, then making this matrix vector product will result in an error. And this is how you fix this. It's also fixed here in the product of A with the vector Q. So this is now the main loop. So in the kth step, we compute the new product. So we are computing with this vector. So we actually have initialized properly here. So the initial vector is a normalized residual vector. And then here you recognize the moves from the Gram-Schmidt orthogonalization. We are normalizing Y, and then we have the stop criterion. We have a matrix with a smaller column space than the number of columns given, we will detect this at this step here. We still continue one more step with the least square solving. And we also do then one last update. Right. Okay, my time is getting a little bit short now. I still have the preconditioning to consider. The exercise here asks you to run this Julia function on a very tiny example. It's our running example that has run through the entire chapter. We can, of course, do this with the normal backslash, but just compare whether the methods agree. In the code, I have not shown the verbose option. You can actually also look at the intermediate data. So the Hessenberg matrix actually get larger and larger. We have seen the residual. So the residual exploits the fact that the residual vector is perpendicular to the column space. You can compute this. All right, 5 minutes left to explain preconditioning. So we have problems with large condition numbers. So the ideal preconditioner would be the inverse of the matrix, but that would be too hard. If we just take the identity matrix, actually we don't do anything. So what we actually want to do is we want to reduce the magnitude of the numbers that we see, and we want to do this beforehand. So we do this also by the normalizations. But before we do the normalization, we do this Gram-Schmidt step, and there will be a lot of round-off if the vectors are actually very large, the vectors that we try to project. So there are two types of preconditioners. They are called Jacobi and Gauss-Seidel, depending whether we use the diagonal or in addition to the diagonal, so the lower diagonal part. All right, so this will be explained by means of examples. So we know how to make well-conditioned matrices. Random matrices are well-conditioned. Let's scale them a little bit off. So we will multiply every element by, so we will multiply the third row 10 to the power minus 8. So we kind of artificially make a matrix that is ill-conditioned. Now the condition number is 10 to the power minus 8. Now, can we improve the conditioning? So we take the diagonal and we are scaling the elements with the diagonal. So here the experiment is kind of set up. We know that we did, we scaled one row very badly, but in general, we don't know which row that is. So we take all the rows. We actually take the diagonal part. And here we take the diagonal part of A, and then we multiply, we make a multiplier matrix. Multiplying the diagonal gives you a vector, but we want the preconditioner is actually a matrix. So we make a matrix M out of this, and the inverse of that will be the preconditioner. You see, by doing this, we are obtaining a matrix. So inverting a diagonal matrix is very simple. So we obtain the inverse, the result is B, and we have now a well-conditioned matrix. It's just not as well-conditioned as the original one, which had condition A, but 20 is still very, very good. All right, 2 more minutes for the Jacobi, the Gauss-Seidel conditioner. I multiplied in the previous experiment a row. Let's do this with a column. And actually, if you do this with the condition number here, the condition number of A after multiplication actually grows. You can be mistaken, well, it's just 3, but hey, that is this, we read our numbers from right to left. So we started with 10 to the power minus 8 as our multiplier, and we have 10 to the power 8. So now the Gauss-Seidel preconditioner will take the diagonal and the lower triangle part. The inverse is solving a lower triangular system. But you see the condition number, there is nothing here at the bottom, at the back, so the condition is now very, very nice. Okay, my time is up. The exercise, essentially, next exercise asks you to do this, but now not with the third column, and now with the first column.